So real quickly, what I want to do is just give me 1 second. Do I have to add it again? I probably have to add it. Mm-hmm. There's a poll feature, which I am trying to figure out where it went. I think it left me. Poll. There we go. Okay. So I'm going to start a quick poll. And basically, I'm going to be focusing on one specific topic that I know you guys are covering. And essentially what I want all of you to do is vote which topic you want me to cover today. Granted, if we have time, we'll cover a few of them. Dung, you said, so if I am in Tasa from session, I won't earn any credit from your session. You will receive participation credit, I think, is what he said. He believes that your attendance to these peer leading sessions are very important. So if you are taking it with him, yeah, okay. So it looks like he might have changed it so that you only have to attend 10 sessions. So there you go. I don't know if he's going to give extra credit. We talked with him. He didn't like the idea. We could still kind of communicate with him. I know Corsova's the main data structures instructor. She's given extra credit for a while now. Has attendance been recorded? That's what I'm about to do. So your attendance in this peer leading session, there's going to be 2 attendance polls. So just for my sessions, I already said this. So if you're joining late, it's no problem. But my sessions, there's going to be 1 session a week. The 1 session is going to be on Friday from, I know I said 11. I might change it to be 11:15, 11:30, just because I have a research meeting before this. So that usually carries on. Usually it's like 45 minutes. Today it was like an hour and 10 minutes. So I don't really want that to kind of cut into our time. The reason why I had it at 11 though is because I know you guys have your TA office hours at 1, and I didn't want to cut into that either. But I think I'm gonna have to, just because this is like the one time I know everybody is available and that I'm also available. Just because it's Friday, and I know a lot of you don't really have any Friday classes. Unless you do, in which case, feel free to reach out to me. I'm going to send out this poll. So this poll essentially is going to dictate what we're covering today. So what I'm going to do is I'm going to be recording all of you who kind of answer this poll. But if you don't answer this poll, then you won't get credited for attendance. So what I want you to do is take a look at the poll and pick your, I guess, weakest area. And if you're not weak in any of them, just pick whichever you think that you want more coverage on, or maybe something that's more new. I know arrays, that's something that you kind of deal with in previous classes. Yeah, what's going on, Jode?
So I don't see like the chats. I don't know why the chats is not even showing for me. So I might not be able to do the poll. Just wanted to let you know.
Does everybody see the poll? You should all have access to the poll.
I don't see the chats and like at all. That's what's the problem.
Okay, it looks like linked lists are really taking the majority. It's awesome. Okay. Okay, awesome. Okay, so we'll spend like kind of a little time on linked lists. In reality, you're not really going to use linked lists a lot. You're going to use a flavor of a linked list. And what I mean by that is there's different ways that you create these linked lists. In in such a way that it behaves differently. A regular linked list is as good as an array. Obviously, you're going to learn about this in the course. Just to confirm, the poll is attendance. Yes, the poll is attendance. So if you don't pick one of those, then you're not going to get credit for today. So if you are attending and you want to get credit, definitely do the poll. I'm going to do another one later. And then I'm going to, what I'm going to do is I'm just going to union whoever answers both of them. So if you answer one now, but you don't answer the second one, that's okay. You're going to get credit for today. If you answer the next one and you don't answer this one, that's okay. You're going to get credit. If you don't answer either of them, you're not going to get credit. Yeah, Joe.
But I don't see the poll for me. I told you.
Raising your hand.
Yeah, I was saying I don't see the poll. It doesn't. Can you hear me?
And Kwali, you guys are both raising your hand. Is there something that I missed?
Yeah, I was saying that I don't see the poll.
I'm going to lower your hand. You could raise it again. Looks like a lot of you are raising your hand. Okay. I'm going to be going through. I'm not going to be taking a look at the actual Teams meeting, but what I will be doing is just kind of like going over on like a whiteboard with all of you. She does not see the chat. That's probably because you are not logged into your USF. Joe, do you look like you're a guest?
Oh, okay.
Yeah. Make sure if you can leave now and then join back not as a guest. So yeah,
thank you.
You want to make sure that you're not using a guest account. That's another way not to get attendance, because I don't actually have an email for you. If your email isn't your USF email, so if you're not logged into your Teams, your USF Teams, you're not going to get credit. That's very important. I'll just type that into chat. If you are not joining on your USF Teams account, you will not get credit for. Because I'm not the one that actually goes through credit for. There's extra credit for coming to peer leading. It depends. I kind of already said that. I'll say it one more time really quickly. If you attend peer leading, depending on your professor has the ultimate authority of how much extra credit you get, if any. So I know for Ramen section, I don't think he said he was going to give any extra credit. We're going to still talk to him as peer leaders. We're going to try to get him to give you guys extra credit. Coursova has agreed to giving you guys some extra credit. Last semester, it was 3 extra credit points on your overall grade if you attended every single session. The whole idea is, like, if you're attending, you're going to get some form of like reward. I know the Ramen section, he's mandating that you guys attend some number. We're going to try to say, okay, if you attend more than this number, then you get extra credit or some form of that. So it's really determined later in the semester exactly what it is that you guys are going to get out of this. So for right now, we're just going to kind of go over the poll that you guys sent, the poll responses. So 85% of you said linked list. That's a lot of you. And that's, I wouldn't say concerning for me, but it's definitely something that I want to make sure that all of you definitely understand before you leave today. Linked lists is something that I know you guys all have to do in program design. So to see that a lot of you are having trouble with them tells me that maybe you didn't cover them in program design. In any case, we're going to go over those today. So I'm going to start sharing my screen. Just want to make sure that everybody can everybody see my screen? Let me just make sure that everybody can see my screen. Thumbs up or anything.
Yeah, we can see your screen. Hey, did you just say poll? Did I just miss the poll? You guys already took it?
Why can't I hear? Hello?
Hi, can you hear me now?
Yes, I can hear you. Yeah. You see my screen?
Yeah, I do see your screen, but I was wondering if I missed the poll. I was having trouble joining the session, and I had one of my friends send me the link, and I was finally able to join. Did I miss the poll for today?
So I said this again, and I'll say it one more time.
My bad.
If there's going to be 2 polls, there's going to be one in the beginning and one halfway through after our break. The poll is for the day. There's going to be 2 of them. The polls for the day are going to get union together. So if your name appears in either of the polls, both of those polls become one poll. And if you can't attend the early session, but you could attend the second part of the session, then you'll get credit for today's attendance. I'm only doing 1 attendance. So if you attend during either session and you do the poll for either session, either part of the session, then you will get credit. Does that make sense?
Yeah, thank you. Thanks for the clarification.
Of course, yeah. So linked lists. Let's just kind of take a look at kind of what we're dealing with linked lists, right? So you have these, like, I know a lot of people like drawing a bunch of circles and connections between the circles. And for somebody who's never seen this before, it's probably a little overwhelming. Like what is this? There's code that kind of goes behind all of this, but at a high level, it's kind of like structuring your data. You have some data in a data set, you have some data in your program, and you need some way to represent it. There's another thing that I would even say is you have some sort of machine that you're trying to build in order to solve some problem. And your machine that you're building relies on the structure or the sequence of how your data is coming into the program. That doesn't make sense? Don't worry. We're going to talk all about it. Okay. So with linked lists, right, we can kind of, how do I change the color? So with linked lists, you have this kind of link between one node. So I'm going to call this node 1 and node 2 and node 3. So you have these links. These links are essentially going to allow you to access a node through another node. Really what you're doing is you're constructing a reference to the memory location of this node. And if you're wondering what I mean by that, I have some node, let's call it node 1, and I'm a very Python kind of guy. So when I think of like an object in a program, it's really just an encapsulation of memory and operations that you can do on that memory. And you can do a lot of operations on some finite chunk of memory that you call an object. So this node is just an object with a non-mutable amount of memory allocated to it. What I mean by that is, let's say you have 2 data fields. Let's say you have an int data that defines your node, and then a node pointer next. Okay, so what we're essentially doing here is defining the amount of memory that this node object will have in a program, right? So this will be about 2 bytes. And this will be about, I think it's 4 or 8 bytes, depending on your system. So I'll say 4 bytes, just to make it simple. And the reason why this can change is, so if you have 32-bit computer, 32-bit, that's 4 bytes. And if you have 64-bit, that's 8 bytes. And really what I'm talking about here is the amount of address space you have. On a 64-bit machine, you have a lot of address space. Your address space is 64 bits wide. That's why on a 32-bit machine, you could only have, I think it's something like 2 or 4 gigabytes of RAM. I don't remember off the top of my head. But on a 64-bit machine, that number is like ridiculous. It's like in the millions or billions. I don't even remember. It's like 32 bits, like 2 gigabytes of RAM, or like 4 gigabytes of RAM. 64 is like 2 trillion gigabytes of RAM or some crazy amount, right? Because you're basically, like, if you look at the difference between these two numbers, right, this is 32 bits longer, which means that, I mean, if you do the math, right, you have 32 extra bits of precision that you could use to actually index into memory, right? And that's going to give you this number, right? Because a node pointer, right, and I know for those of you who want to refresh in pointers are really important to really understand for, I guess, data structures in general, but specifically these types of data structures. A pointer is just a reference to another location in memory where an object may be. And your pointer can be usually one of two things. It could be used or non-used. And usually when you have a pointer that's not in use, it's equal to null. Hold on. Let me just... Okay. So if you have a null pointer, then that means that you can't index into a next node, right? There's no way for you to get to a next node. And that's something in your program you would have to account for. Just for this case, right? Node 1 would have 2 data fields, right? So the size of node 1, you could even think of it as having two data fields, right? We have 2 bytes and 4 bytes, right? We're using a 64-bit machine. So just looking at the memory at node 1, you're going to have some data. So I'm going to say, let's make it have 3. Let's make this have like 7 and this 10. Why not? So here, it would have at index 0. So you basically go 4 bytes, and that would hold the value of 3. So it would look something like this. And then directly after that, you'd have another 4 bytes. I said 4 bytes here. I meant 2. Let me erase this. I was thinking of an int 32 eraser. You're gonna let me erase? No? Can I select it and delete it? Give me 1 second. Nope. Why can't I erase? I guess it is erasing, and the background is black. So give me 1 second. I'm just gonna fix this somehow. Colors, main color. Make it white. Color this in. So this would be 2 bytes, and then you'd have a 4-byte address. So this 4-byte address, whatever it is, it doesn't, we're not going to concern ourselves with it. It's going to be pointing at the address of node 2. And I could tell you that based on this diagram, right? I'm going to even get rid of this. So I know we kind of jumped ahead a little bit, but I'm going to get rid of these kind of like backwards connections, and we're just going to focus on these forward connections. Okay. So let me go back to black. Okay. So you can see right here, right, this node 1, it has 2 bytes allocated for the int and then 4 bytes allocated for the actual pointer, right? So this is something that you would have in your memory. And if I were to have access to the memory of node 1, then I can do something like node 2 is equal to node 1 dot next. Right, so this is node 2. By the way, I'm going to scribble that out. Node 2 is equal to node 1 dot next, right? What we're doing here is we're going into the object containing node 1, and we're pulling out this piece of memory. It's really important. And I don't want to go too deep into the memory layout of these programs, but it's really important that you understand that in C, everything is memory, right? You don't have like a bound on the way you access memory, right? And what I mean by that is you access memory in C++ the same way you would access memory in an assembly program, or at least you can, right? Which leads to a lot of bad things, right? It leads to a hard time programming because there's this idea of, like, I guess, type safety, where in like a type safe program, you can't just access memory. Everything is kind of just references and objects. And I think one of the hardest challenges about actually using C++ is this memory management. But for right now, right, let's forget about the whole idea of like just using memory in like what I said, right, type safety. Forget about that. What you really have to understand is that these objects are going to be allocated in a location that requires you to understand, at least at bare level, what kind of memory you have. What's your memory layout? Because if I allocate this N1, let's say on the heap, right? If you have two locations, right? I'm gonna draw my memory. I want to extend this page. So I have my memory. In your memory is consisting of two things, the stack and the heap. So your stack is where all of your basic program data goes. The heap is where you're allocating memory, and you're basically using those allocations in your program such that it's not going to just get cleared, right? There's no collection of the memory. The stack you could think of as dynamically growing and shrinking based on the execution of the program, right? So let's say I had some function call, right, to function. What I'm going to do is I'm going to throw all of the parameters for that function call on the stack. So maybe P1 and P2. Those are going to get pushed to the stack. Then anything that function allocates, like say like declares like a variable, say function, let's say int P1, int P2. And in this function, I wonder, can I extend? Let me try to extend. Okay, sweet. So I'll just do it here. Okay, let's just quickly write out the function. I'll do the memory again. Stack, that's growing downwards. And then you have your heap that's growing upwards. Say you want to call function. So you pass P1 and P2. And then we'll kind of get back into this. So we have our, let's just say void function int P1 and then int P2. Your P1 and P2 are going to get pushed to the stack, like I said. But anything inside of this function is also going to get pushed to the stack. So if I say int v1 is equal to 5, right? Why not? And then ... I return, right? At this moment in the program, the 5 is going to get pushed to the stack right here. And v1, right? So at this point, all of this data is on the stack like this. And you have more stuff on the stack, right? You have main on the stack. You have other things, right? Where did you actually call this function from? If you called it from main, then it would just be main. But let's say in main, you had a function called foo, and foo called this function. Up here, you would have the foo stuff, right, before you actually return back to main. When you're calling functions, right, and this kind of goes back to that recursion. I know you guys are dealing with recursion, but forget about recursion. This just applies across the board. When you call this function, these parameters are getting pushed to the stack, and as soon as you leave, they're gone, right? That's the whole idea of scope. When you return from a function, all of the memory associated, the declarations, the variables associated with that function leave. You don't have access to them anymore. And the reason is because this stuff all gets purged. So when I return, right, I'm going to purge this from the stack. And we're going to move the stack back to the place that it originated from. Essentially, you keep track of where the stack is. When you call a function, you extend it, and then you shrink it back down when you return. And the idea is you don't want to let memory stay on the stack. You want to decrease the memory that you're putting onto the stack by kind of decrementing it with where the program currently is. And if you're calling function from main, when you return back to main, you don't need this stuff anymore. It's gone. So essentially, that brings up this paradigm of having to allocate our memory on the heap. And that's something that a lot of people don't necessarily, it's something that I know a lot of people don't want to have to deal with, right? How do I know that, like, when I allocate this variable on the heap, when to actually deallocate, right? The whole idea of destructors and constructors and freeing memory, and it becomes a lot to deal with. But I will say this. When you're allocating memory on the heap, you as the programmer have to actually understand, okay, this is my data. This is my node, right, that I'm trying to allocate. I need to do two things. I need to either A, when I construct this, allocate the memory I need to, or B, deallocate the memory when I need to, right? So what I'm trying to get at is your node will only hold the data that you require it to if you manage it correctly. If, let's say you wanted to get rid of, I'm going to copy all of this, and I'm going to create a new one. So we're going to zoom in on this, and we're going to go back to here. Okay. Let's say I wanted to remove node 2 from the program, right? But if we just kind of, let me kind of get rid of some of this stuff. What is this? Free selection? No. What do I want to do? Can I delete this? I can, but it gets rid of the white background. Do I have any other tools that I could use to extend this page? Maybe I can crop more. No.
So many use cases here.
Yeah, I'm gonna have a different drawing software next time that is a lot better. I thought this was like Paint, where you can just kind of extend the page as you go, but I don't see anything to do that. Has anybody ever used the basic like Paint clone for Linux and knows how to extend this page? No. Okay. I'm just going to continue from here. I'm going to try. Tools. Maybe I could just scale it. I could scale it, but can I fill all of the rest of this? Pencil options. I don't have like a paint tool. What is this? No. Okay. Okay. I'm just going to go back and redraw this here. So essentially what we had, right, we had the construction of 3 nodes. We had what is going on? Okay. Okay. Okay, there we go. Okay, we had 3 nodes. We had node 1, we had node 2, and we had node 3, right? So this whole idea of memory becomes really important, right? Let's just assume that we have our heap, right? We could forget about the stack for now because it's not going to affect us. Let's just assume we have our heap and our program is running and we are allocating these nodes onto the heap. So let's just draw this. So these nodes are all going to have their own unique memory addresses. If we connect these nodes together, essentially what we're going to do is take, right, the object and basically construct a reference. So our next is going to be N2. We said this is 3, this is 7, this is 10. So awful 3, but I'll just do D is 3. Here I'll do D is 7. Next is node 3. And then here we have some sort of same thing. Here we have node 3, and node 3, let's just say D is equal to 10, and next is equal to null pointer. Right, super important that we kind of just declare that. So essentially what we have here is a bunch of memory allocated on the heap, right? And if you remember anything from the class, I don't know if they taught you this, they should have taught you this. If they didn't, then I just hope this isn't the first time you're hearing this. The stack, like we said, has garbage collection. The garbage collection is based on where you currently are. So if you have some function, like we said, foo, right? If you have, let me just kind of move. If you have function fn, right? You have your fn function. Your int v1 equals to 5 is going to get garbage collected. That's that whole idea of clearing this from our memory after we're done using it, right? So this v1 doesn't permeate and cause us to lose valuable memory space. Super important because the more you lose your memory space, so let's say you have like, I don't know, I'm trying to think of a good example. Let's say you had like a bunch of web pages and you were trying to keep track of the history, right? So this page brought you to here, this page brought you to here, this page brought you to here, right? You're trying to keep track of all of them. Let's say you clear your history. In a good garbage collection, all of the memory references for this would be gone. But in our case, right, in a bad garbage collection, so the programmer wasn't actually implementing proper garbage collection in the program. They decided that they would get some benefit of using C++. They thought that they were really good at doing the garbage collection, but they had one mistake. The more that user uses the program, the more memory is going to be used. So if you guys ever open up your browser or your task manager and you just take a look at Chrome, I'm not saying that Chrome has a problem keeping track of the history. It's not necessarily that, but Chrome is really bad garbage collection. So if you ever reset Chrome and then reopen it, I don't know if it might not even be like this anymore. I know it was like 5 years ago. The longer you have it open, the more memory is going to get leaked. And like basically when you have a memory leak, it's data on the heap or data somewhere in memory that doesn't get deallocated, which is a super big problem. And the reason it's a big problem is because when you have these areas in memory that go, your program keeps growing, right? I think even like video games, right? If you have a video game where you have constant stream of new objects or entities, right? Let's say like you're playing Grand Theft Auto 5, and you're trying to get that to run on like an Xbox 360. Your assets, your references to like the players that are moving around on the screen, if those stay in the memory, let's say you never deleted any of them, that game would probably run out of memory space within the first, I don't know, like 30 seconds to a minute, running on like an Xbox 360. And that's because the Xbox has a lot more limited memory than like a larger computer. But it's also because GTA 5 has all sorts of tricks to clean that memory every like 5 or like 6 like iterations, right? It's constantly getting rid of items it doesn't need. And that's why it's actually able to run on the Xbox 360. So as a programmer, knowing how to actually manage the memory, super important. So let's talk about a very simple algorithm called, I guess, removal of a linked list. So you have your linked list. You're trying to get rid of this one, right? And also do a good job and get rid of its memory allocation here. So we'll just do N1, N2, and 3. So the process of removing some sort of node from a linked list, the first of the process is basically get a reference to this node and this node, because we want to maintain our list, but we also want to make sure that we completely get rid of node 2 without having any problems afterwards, which means we have to get rid of this connection, this node, this connection, and this connection, and repair the connection between the rest of the list. So there's 2 parts. So we need to get a reference to node 1, get node 3, and then what we need to do is obviously get node 2, but I should have put that first, get node 2, and obviously get node 3, right? Obviously flip those would have been better. The good way to do this would be first to set the reference here equal to null. So our n2 dot next is equal to null pointer. Basically, we're removing it from the list, right? This node no longer exists as a component in our list, except because of node 1. So then what we would do is we basically restitch. So we'd say node 1 dot next is equal to node 3, right? So we're basically joining these 2, right? We're discarding. Let me just. We're discarding. I'm trying to think. Node 2 dot next. We're discarding this connection. We're also discarding this connection, and we're creating this connection. The last thing you would need to do is essentially, okay, so we have these 2 connected. The last thing we need to do, right, because we're good programmers, is actually get rid of node 2. So then we need to delete node 2. Okay. This is kind of like a high level description of what you would do, but there are a few more cases. I'm just saying for this list specifically, we could identify this set of instructions. But let's talk quickly about what it means to delete node 2. If we wanted to delete node 2, that means that we shouldn't delete any of the actual outgoing references unless we know that they need to get deleted. And that's why linked list and memory management gets kind of hard, right? Because it's not necessarily clear, like, do we delete this reference to node 3? I know we removed it as a reference, but let's say we didn't. Do we delete that reference? And the answer is no. Because as a component of our list, we need to have a very good way of actually deallocating the memory of node 2 and not affecting any other structure. This is going to be something that all of you will struggle with on your programming assignments. If not this one I obviously would say is probably a lot more simple. Definitely the tree assignments, definitely the graph assignments. You're going to have to keep arbitrary lists of nodes and actually deleting the references between these nodes while they're all allocated on the heap is going to be challenging. So it is very important for you to understand this here, right? You don't want to affect the overall structure of your list. That's like square one. And if you're looking at this and you're saying, I already know how to do this, that's good. But the reason why I'm kind of bringing this up is because in the future, you're going to affect the structure of your data structure when doing the assignments and run into problems with actually, like, you're going to run into segmentation faults. You're going to run into issues with the program running, and you're not going to know why it's breaking. Right? Why is it breaking? The one thing I will say, other than obviously like basic errors, like you forgot to set this connection, right? That's why it's breaking. The one reason why it might break, and you would have no idea, and you would be frustrated for hours, is because for some reason, somewhere in your code, you affect the structure of the list or the data structure without intending to do so. And that's kind of this idea with data structures, right? It's supposed to teach you to get really meticulous about how you're doing these operations. So I'll give you an example of like breaking. I'll give you an example of actually like what a destructor would look like for a node, right? So say you had some node class, and you wanted to, I think it goes here. Let's say you had that data in that node pointer. You would do nothing. That's your example. And the reason for this is because your node class has nothing to free. The difference is when you're deallocating an entire list. So let's say we had some function, right? Dealloc linked list. And you had some node pointer head. The reason I bring this up is because obviously this is going to look a lot like something like a linked list class. So maybe your linked list class is here instead of this dealloc. So instead of, you would have like squiggly line L list and then nothing here. It really depends on how your program is structured. Obviously, for most of your assignments, it's going to have the form of this. This is something that I see a lot just working on code, just like basic functions to deal with this stuff, just because do you really need a class for a bunch of nodes? Maybe. It depends what you're using them for. A lot of times, no. But with this, what we're going to look at is actually how you would go through and deallocate these without breaking it, without having any memory leaks. Because not having a memory leak is super important for your program. Let's do this real quickly. Let's just create a new okay. So I'm going to create a list, and I am not going to name them anymore, or I'll name them. I'm not going to give them any values. But you'll see this thing, and if you're not used to it yet, then you're going to get used to it very quickly, at least as a student here, node n. So I'm just saying like dot, dot, dot. You have like some number of nodes in your list, right? This method should work for all numbers of nodes in your list. So essentially what you want to do is you want to go one at a time. So there's two ways to do this. You could remove this and then keep track of this. You could remove this, or hold on, I'll take that back. And then deallocate this. So essentially collapse, keep a reference. So you always need a reference to your whole list. You can't get rid of your only reference to the entirety of the list. And you have to do this process one step at a time. There's no like quick removal of memory like with an array, right? An array deallocation is super easy, right? Just delete array, right? Super simple. For a linked list, it requires a slight amount of more meticulous structure to how you do this. So what do you actually do? So basically you have I'm gonna create a loop for this. So I'm gonna say loop. I'm gonna say while the current dot next does not equal null pointer. I'm not programming. I am kind of saying what the logic is. So don't worry, like this isn't actually a C program or a C++ program. I'm just kind of demonstrating what the program would kind of have to do. So while your current dot next, right, is not equal to null pointer, obviously your current is equal to the head. And obviously this is a node pointer. I didn't specify that, but you should be able to take that out of this. So your current is obviously a node pointer. Your head is obviously a node pointer. So while your current dot next is not equal to node pointer, you're going to do this. You're going to say previous is equal to current. Current is equal to current dot next. And at this point, we could get rid of the previous. So in this case, we would say previous dot next equal to null pointer, and then delete previous. So essentially what this is doing is it's going through each of these. It's basically has two pointers. It has one here, and it's basically and here you would cut this node out and do this thing, and then cut, and then all the way until this. And this is your terminal case. And in this case, right, let's just kind of look at our loop. The next node is no last step, right? So I'll kind of add that as a note here before we take a break. Terminal delete current. So essentially what I'm just saying is in the terminal, like the last piece of this loop, right? So once the loop has terminated, you would then delete the current node. And then your entire list is deallocated perfectly. And really what I'm trying to demonstrate here is that at any time you still have a complete linked list, right? This works also if you just want to delete node 1, right? You just increment this pointer here and you delete node 1, and now you still have a full complete linked list. Your full complete linked list is just node 2, node 3, blah, 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 all the way up to node n. And you haven't actually you haven't removed the structure of the linked list by doing these operations. You've just done exactly what you said that you wanted to do. You wanted to delete the first node in the linked list, and you want to delete it all the way up to the end because you want to deallocate all of them. So you could only delete one node at a time in this case, because if you delete more than one node, what you're going to end up doing is removing the structure, and then you would have a memory leak, right? So if let's say we tried to delete both of these, so now we don't have any reference to any future of this list, right? So let's assume in this case, we also deleted node 2. And then we come back up to the top, and now current is equal to null pointer because we deallocated it. And now we don't have any reference to node 3, and we don't have any reference all the way up to node n. So all of this ends up on the memory, on the heap. It ends up just left in memory on the heap, and we have no way to actually remove it from the memory ever again. This is the prime example of a memory leak, right? We have no way to reach this section of memory, and it has basically plagued our program. We can't access it anymore unless we do some sort of magic. There's no real way to actually access that memory. So really what I'm trying to demonstrate here is at any time you need to think of the steps required for you to do something in a way that's going to remain, it's going to leave you with the remaining memory in your program, access to all the memory. If you are allocating variables, you don't want to ever lose access to that if it's going to live in your memory. So you could think of what I'm trying to get at is here. If at any point you lose track of memory, and by lose track, I mean you can never reference that area in memory ever again. Think of objects. I can never access node n ever again because I don't know where it is. I don't know where node n exists. I can't just pick a place and hope that I found it. You need to definitively say node n lives at this address in the heap and then delete it. And the reason for that is because if you don't, you will lose track of all of your memory. I kind of already said that. But really what I'm trying to get at here is even if you don't have node n as a variable, you can access it through this entire linked list, starting at node 1. And in the event that I need to delete node n, I have access to it through node 1. If I lose access to it, then I've created a memory leak. I'm going to open for, do we have to set node n.2 next to null, or can we just have a node 1 next point to node 3 and free node 2? It depends how you're freeing node 1 in the node. It depends how you're freeing the memory. So if we go back to that real quickly, if you're freeing the memory and freeing the memory frees the, I guess, node here. So let's say that your destructor for node 2 ends up calling the destructor for node 3. What do I mean by that? Well, you're in the deallocation for node, and your deallocation for node accidentally deallocates node 3. This case, you will end up removing node 3 from memory, causing some sort of potential for a segmentation fault, which will break your program. Happens all the time. This is a prime mistake. What I like to do is I like to basically zero out any references that node might have in order to remove its ability to even do this. And when I say like in this case, it's really simple. It's really easy to see that that's not going to happen. In more sophisticated or like complicated cases, you might not necessarily see that node 2 deallocating it is going to deallocate other memory that you want access to. So you might end up eventually running into a segmentation fault by not even realizing it. So as personally, what I like to do is I like to deallocate all references to other memory that I want to remain in my program, like node 3. I don't want this to have any access to node 3 if I'm going to get rid of it. And that's just me being a safe programmer. I recommend this as like a technique, I guess you could say, for all of you, just because for me, I've ran into problems, and I also want to help all of you not run into problems. That's kind of the outcome of peer leading, right? You guys should take some of the problems that I've ran into. You should take kind of like the knowledge that I've been able to kind of accumulate throughout my time here at USF and use it to do better in data structures, right? How do you do better in data structures? You hand in the assignments, perfect scores. How do you get in the assignments with perfect scores? You avoid you avoid program breaking errors, and that's really the main focus of peer leading. At least for my sessions, is just going to be getting all of you to be able to actually really program all this stuff, especially the things that you aren't necessarily comfortable with or having trouble with. So for right now, I am going to say we should take a 5-minute break. So we will reconvene at 12:24. I know that's a little longer than 5 minutes, but we're going to reconvene 12:23, 12:24. And when we reconvene, we're actually going to get hands-on coding experience. So if you are feeling like you don't need a break, what you could do in the next 5 minutes is open up your terminal and open up a new CPP file. And we're going to get, if you can, put me right beside your screen and we could just code together. And we're basically going to program some linkless stuff. So like I said, 12:23, 12:24, we'll reconvene.
That's a quick question. Questions?
Sure.
Hi. For your algorithm, wouldn't it cause like an error? Like, because if there's like a point where like the current is like current.next, it would just leave the node that's just before the next one. Unless it's actually what you wanted. Actually, never mind.
Are you talking about this one or this one?
The one with the while loop.
This one.
Oh, okay. Oh, yeah.
So basically what this loop is going to do is it's going to terminate us on node n. So on node n, this becomes false, right? So current.next is equal to null pointer. In this case, you just delete the current. You don't need to do this logic right here.
All right, so like,
does that make sense?
Yeah, you just wanted to leave like one node behind. Is that like the?
Yes. Yeah. So you're basically lagging one node behind. So for node 1, if I delete node 1, I basically need to set the current equal to this node, and then I could delete the previous, right? So we're always deleting the previous.
All right. And then actually, so, if I can ask about like assignment 1, right? It's like for Kursova's class, right?
Sure.
Let's see. Where do we write our code? Do we write our code on the provided C++ file or the?
Yes. Yeah, you're gonna write all of your code in the provided C++ files that she gives you.
So like where the test code is, I'm assuming.
No. Okay. No. So my bad. You're gonna be writing all of your code in the actual project files.
Uh-huh.
So you're gonna so essentially what you're gonna do is you're gonna write. We could pull that up. If you want me to.
Yeah.
Let's go. I think it's this one. Ordering. Oh, it looks
Yeah.
like she changed it. She changed the first one, it looks like. That's the first. Okay, so let me just open this. Okay. I'll do this. Extract. I'll open this in the terminal. Okay, so I don't know if I could zoom. Should be able to zoom. I don't have my mouse connected, so. Let me zoom in again. Okay, so if I just kind of show you these files, the int D list, I didn't actually look at this assignment. I was assuming she was going to have the same assignment as last year. So this is kind of where you're going to be including your code. So it looks like she gave you a code, like a header file to use, and it doesn't actually do anything. The other file she gave you, it looks like, is probably for your linked list. So this is kind of like where the logic that we were just going over would actually reside. What you would be doing is you would be doing something like this, right? You'd be doing something like nano, what's the int dlist.cpp, and on the first line you'd basically say include int dlist.hpp.
So we add our own C++ file then?
Yes, you're creating your own C++ file. So when you're
Okay.
looking at your directory, you should have int dlist hpp, int dlist cpp, int dlist hpp, int dlist node cpp. Does that make sense?
Yeah. And that's like that works. It doesn't like mess up anything with the catch file or anything like that, or
As far as I'm aware, no. Yeah, because she's including your header file. And if you do it correctly, if you compile, which we can go over in just a few minutes, it should basically compile everything correctly.
all right.
We'll talk more about compiling if you want. Like, I don't know how much code practice all of you have had with C++. Maybe we'll make that the polling question for the second one. But I'm gonna take a real quick bathroom break. It's 12:23. We'll start again in probably like 3 minutes. And when we come back, I'm gonna have a poll question for all of you, and we're going to do some programming. Can all of you guys hear me? You can give me a thumbs up if you can. I'm just trying to. Looks like we have a hand. Yeah, Gianna. You're just showing. If you have a question, feel free to ask. Otherwise, I'm trying to get this poll to go. It's not letting me. Something's going wrong with the polls. If that's the case, I'll try to do it again at the end. I don't know. You can hear us. You can hear me. Okay, awesome. I'm going to try to refresh. Okay. Okay, so it's still recording. I'm going to share my screen again. I'm going to try to do the poll one more time. If it doesn't work, then I don't know what to do. I'm not going to spend too long fighting this. Looks like it might just be a problem with Teams. If that's the case, then we'll just continue. Okay, so which one did I? Okay, this one. Okay, so please react. I'm going to have two messages. Please react to the message. If you react to the message, then I could probably go back and just count you as attendance. So what I want you guys to let me know is, so for programming, do a smiley face if you want me to focus on C++ syntax and development, and do a cool face if you want me to focus on just algorithms. So the stuff that we were kind of working on. So please react in the way. Hopefully you can. You should be able to. Yeah, so if you're having trouble more with like the syntax and the actual creation of C++ programs, we'll focus more on that. I'm hoping by now you have some experience. So I want to focus more on the actual algorithm piece, but it's up to you guys. Either works for me. And remember, this will act as your attendance, unless I can fix the polls. It's really close. A lot of you want to focus on the syntax. A lot of you also want to focus on the algorithms. So I will give that another 30 seconds.
Actually, okay. For this class, do we need to cover a lot about like enums or no? Or do we just ignore those for the
I mean, I don't know if you're going to get tested on enums.
okay.
Enums are good for programming.
Is it just like a list of macros, I'm assuming, or
Basically, yeah, it's just like it's basically like, you can think of it as like classifications. So let's say you had an enum. Let's say you had an object and you had like 5 different types of objects, maybe like a red object, a green object, brown object. Now I'm talking about colors. So you could think maybe color is like a good way to do an enum, right? Red, black, green, blue. And then you'd have like a value that represents that classification. It's useful for specific applications, especially like, I don't know if her project right now is dealing with this, but her project in the past has her project in the past has been something along the lines of like, you have to deal with like plus add, so you have to deal with add, subtract, divide, multiply, modulus operations on like on a linked list. So having like a like an add, I guess you could say, enum, or like an operation enum was something that I used for that project. So we're going to focus more on the actual programming, C++ syntax and development side of stuff. So we're not going to really focus too much on the actual program. So, wait, did I answer your question?
yeah, it's just like it's useful for some things, but we're not really gonna be tested on it.
It's nothing. It's not like it doesn't add any sort of like. It's not something that you'll learn in data structures, because data structures was more focused on how you organize data in a program, and how do you manage your program. Like, if you think about it, like from like a naive perspective, the reason you go to college is so you're better than the people that went to boot camps. The people that go to boot camps, they learn about naive ways to do stuff. So triple for loops, without any kind of like analysis of the structure of a program. The boot camps will kind of show you how to code, and they'll show you how to solve problems from naive approaches. If your goal is to solve a problem, if your goal is to solve a problem the best way possible, you take data structures and you take a rigorous computer science slew of electives, like maybe like intro to AI, compilers, maybe even like some theory electives like automata. Like you want to build up your knowledge of problem solving, and data structures focus more on that. So what we're going to do, I'm just going to create a new folder for this this session. And what we're going to do is we're just going to create a simple linked list. So we're going to have 2 classes. We're going to create our node class, so node.hpp. So in this class, we're not going to really have anything crazy. We're just going to have a class node, And our class node is going to have two data fields. It's going to have an int data and a, what is that called? A node pointer next. Same stuff that we've been dealing with. I'm going to delete this. Maybe I'll delete this. So the first thing that we need to do is actually define the constructor. Make it bigger? Sure. View, zoom in, view, zoom in, view, zoom in, view, zoom in. Is this good? Yeah, if you have somewhere to be and you've been here, then yeah, you don't have to stay here for the entire session as long as you do the attendance. I'm not gonna impose hard attendance restrictions on you guys. Obviously, you have somewhere to be. You have somewhere to be. Okay, so what we're gonna do is we're just gonna create a simple constructor for our node. So let's just say we have our input to the node to create it is just some value for the data. So what we're going to say is data like this. And essentially what this is doing is it's passing the value of D into our data parameter like this. The next thing that we're going to do is we're going to I'm going to have two constructors. Maybe that's a little we'll demonstrate what I'm talking about. Node pointer next. So in this constructor, we'll create both of them and we'll do nothing. Okay. So that's a complete constructor. The second constructor will just be some value. Do we need to specify private or public? You do. That's a good point. So this would be public. And all of this stuff is private by default. You could make it public. I think I'm going to make it public. I think I'm going to make everything public. In your assignments, you might not necessarily have this. You might have something else. You might have to have private data fields and have setters and getters. If you do, I mean, I could show that. I don't know if that's too important to focus on. Right now, I'm just going to make everything public. Doesn't really matter. Understanding public, private, and protected is also really important, but I think that's probably something that you would cover independently and not what you'd cover with just linked lists in general. So what I'm going to do with this constructor is I'm just going to call the node constructor on D and null pointer. And I'm pretty sure this is the right syntax. Let me just verify. Is this proper C++ code? So one thing I will say, if you guys aren't using generative AI, do your tasks, right? If you have some task and it's involving programming and you don't know how to use generative AI, then you're going to be at a very, I would say, big, large disadvantage. It shows here, yes, this is another constructor. So basically what this is telling me is that these are proper, these are valid, this is a valid C++ program. And it's intended to do exactly what I'm trying to get it to do, which is basically, I'm going to go back here. Basically, what I'm trying to do is call a different constructor from a kind of substructor. And the substructure basically uses this as the overall constructor. So this sort of thing works usually when you have data classes. Data classes, this is really useful. There's other types of classes where like your constructor has to go through some sort of long list of steps. Probably not in this class, but definitely if you ever become like a C++ programmer for a living, we love ChatGPT. Yeah. If you ever become like a C++ programmer from a living, you'll understand kind of more what I'm talking about. So our node class is super simple. We just have a constructor and we have all of this. The only thing we need is the destructor. So how do we destruct our node? We just do nothing. Okay, so save x, just make sure it's saved correctly. So our node is good. Now, what do we have to do besides this? Well, now we have to actually make our linked list. So let's just nano list.hpp. I'm going to say class. I don't think I need any includes class list. I actually forgot something, and we'll go back to it in a second. But class list. This is going to have a private section and a public section. In the private section, we'll have a node pointer, reference to the head. In public, we'll get there in a second. What we need to do now is actually include node.hpp. Right, so we're going to include node.hpp, but then we also want to do one thing which all of you will get into a mix about, is header guards. So a header guard is really important. So our header guard prevents circular loops. Okay, so what does a header guard look like? Header guard looks like if not def list hashtag define list. And then we come down here and we say hashtag end if. Okay. So what is this saying? This is saying, okay, if we haven't defined a file or a reference for our linked list, then we're going to define our reference to the linked list, and then it'll start executing all of this code. You can think of this as conditional code execution. And this code will only get executed once, because if you haven't defined this variable, if you run this, that variable will always be defined, if that makes sense. So you'll never enter a loop where like you kind of include something and then here you include something and now you have two things that include each other, and then you kind of like come here, right? So we'll kind of go through like an example. Let's say our node class included our linked list class. Yeah, so you can think of it like this. When you're parsing, what you're going to do is you're going to include node HPP. Includer is going to stop and say, okay, now I need to go import that file. So it's going to go to node HPP. Let's say in node HPP, you included linked list.hpp. So then it's going to go, oh, I need that. And then it's going to come back in here and it's going to go like, oh, I need node HPP. And then node HPP is going to go back and back and back and back until you basically break the compiler. That sort of stuff happens all the time. So I thought I would mention it. Best way to prevent that from happening, use header guards. Okay, so what we're going to do is we're going to define a linked list. So list, I'm not going to do that. List, and we're not going to have any sort of constructor. We're just going to say head equals null pointer, right? You can't create a list unless you can't actually create a list. You have to kind of go through the methods of the class. So our linked list, it's going to have a few methods. So the first method is going to sorry about that. I accidentally just exit out of the browser completely. So let me just start sharing the screen again. Awesome. Okay. So what we're going to do here is we're going to basically define two methods. We're going to say void add node. And what do we need to make a node? We just need int data. And we're going to have another method that says delete node, void delete node, and it's just going to have the node. I'll have a Boolean here, so we'll say bool delete node. And then finally, we'll have another method. I want to say, so linked list we won't define it yet, but we'll mention that it exists. Okay, so if I try to now compile these, I have nothing to compile, right? If I look at what I have, I just have a bunch of header files, right? You can't have a program based on header files. So what you have to do is define the CPP file. So if I just kind of look at these files, I have this node class. I'm going to quickly add a header guard to this class. So hashtag, I'm going to say header guard. Hashtag if not defined node, hashtag define node. And then we're going to come all the way down here. I'm going to say hashtag end if. Okay. So we have a header guard. Now if, oh, no, wrong file. Okay. So we're going to do more linked list. And you can see our very simple linked list class, right? We're going to be able to add nodes. We're going to be able to delete nodes. We're also going to be able to destruct. Can I split the terminal? I think I should have been able to, but I don't know if I can. So I'm going to do. I'm not going to do anything like that. Okay, I'm just going to kind of copy this and add it as a comment in our next file. So I'm going to clear this and then just say nano linklist.cpp. Okay, now we have our CPP file. I am going to make a giant comment. Just basically demonstrating all of this. No, copy. Okay, and then here I'm going to paste. Okay, I just kind of want to look at it just to make sure that we cover everything. Okay, so now what we're going to do is we're going to include our linked list.hpp file. So what this should do is it should basically, at this point, this should be in the file. The next thing that you want to do is start defining these functions, right? So head, I mean, this is already defined, but our void add node and our bool delete node. So we're going to do two things. We're going to define add node, and we're going to define delete node. So to add a node, I don't think we went over this. It's a little bit more complicated than what you might. It's not as simple as just adding a node, right? There is a little bit of logic. So let's just kind of go over it. So to add, maybe I can do something like this: add node. Step 1, you need to check if head. Step 2, you just need to find insertion, position, insert node. Okay, check if head. This is our base case. I'll call this. This is the base case, not the base case. Forgive me. Maybe like case 1 or default case. I'll just call this case. Find the insertion position and insert the node. So really what I'm saying is we have a base case. If we don't have a head, we need to define the head. Otherwise, we need to insert the node into the list. So that's going to look something like this. We're going to say void linked list : add node. Okay. And this is going to be int d. So you might be asking, what are these? If you haven't seen if you haven't seen C++ code yet, this might look confusing. Really, what you're saying here is this C++ file is going to define the function that will be used on the add node call, right? So when I call add node, this code will be executed for the linked list class. So when you compile this, this gets converted into machine code or assembly code. If you guys did assembly, I don't know how far you got into it, but this will get compiled into assembly code, and from that, the generated code, it'll basically have a pointer to like for the linked list class. Like here is a pointer in the program memory, right? That you're going to jump to, that you're going to jump to when you're calling the add node function. Okay, so if that made sense, 5 minutes left in your meeting. I'm going to say ignore this. We're going to run until 1:15. So it defines the variables and then checks to see if it's already defined for running it. Okay, yeah, that's an old comment. Okay, so here, what we're going to want to do is basically just implement this logic. Right? How do we implement this logic? It's not as complicated as you might think. Obviously, for most of us who haven't had like a lot of programming experience, especially in C++, you probably need a place to start. So where do we start? We start with the base case. So our base case, like we said, was head is equal to null pointer. So we're going to say if this head is equal to null pointer, right? Because we are on the linked list class, and the linked list class has a head parameter. We're going to run this code right here. So in this case, we're going to create a new node. So we're going to say this head is equal to new node. And this new node is going to take in one parameter. That parameter is going to be d. And that's it. That's the base case. The other case, I wonder, I can't modify it right now, but maybe I'll modify it later. The other case is the else where this is kind of like the default case, find and insert at end of list, right? Super simple linked list. We're just going to insert at the end of the list. How do you do that? We're going to say node pointer current is equal this head. Okay. Now that we have the current, we're going to say while current next does not equal null pointer, this current, or current is equal to current next. Okay, and now we have our current to where we need to get it to. In this case, right? So our current is acting as kind of this temporary. So if I kind of go back to this picture here, we have all of these nodes. We have a head node. We have a bunch of nodes in sequence up until the last node in the sequence, right? And then this one, just nothing, null pointer. This one points to null pointer, right? It's not pointing to anything. You start at the head, right? You're basically going to say, okay, my node is, my insertion point is going to be at the end, right? Wherever the first instance of null pointer is going to be. Now, how do I get there? I just iterate through these until I get to the node that tells me that its next is equal to null pointer. At that point, right, your current will be equal to that last node, and then I could just simply set current next equal to new node d, and that's it. This is your entire add node function. Obviously, if there's more sophisticated things going on with your node class, or if there's more things that you have to do when adding a node, those would all go here. But with the construction that we have to add a simple node, really easy. I'm going to say bool delete node int d. Okay, so similar base cases, but these are a little different. In our examples, right? The example that we gave was here. Essentially, hold on. Essentially, this is what we call an in-list deletion. There's 3 deletions depending on. There's really two types of deletions, same as the last, like add. But if you had like a doubly linked list, so these were going here, and these were going here, there would be a few more deletion operations, or at least a few checks that you need, right? So if you're deleting the tail of the linked list, and you are essentially, I'm trying to think. If you're deleting the tail of the linked list and you are trying to set node 2 equal to this, you would need to make sure that you're not like setting null equal to n2, right? You can't dereference null here, so you wouldn't stitch it like this. So n3 wouldn't get stitched back here if n3 was null. I hope that makes sense. I can clarify if somebody needs me to, but I'm just going to continue here. So here we're going to define delete node. So the first is going to be check if head base case, and if the node is the head, then If the node is the head, then what we're going to need to do is kind of just drop the head and then move the head to a new point. So drop current head set to next in list if exist, right? Because we might just only have a head and we might be deleting the head. The second option, or the second case, is an in node deletion. I mean, in list deletion. That's including the tail because we only have a singly linked list. In list deletion. I'm going to say we're going to drop. We're going to do exactly what we kind of said. Get refs prev next stitch together back together if next exist, right? The last case, whether you want to call it a case or not, is node not exist, return false. Okay, so here's what we're going to do. We're going to start by, like I said, check if this head dot data is equal to d. Okay, so I'm going to really quickly mention this because I know that this is complicated, right? Why am I not doing this instead of this? And this is something that I would tell the program design people, not necessarily data structures. The reason for this is, so this is assuming that data is an int pointer. This is assuming that data is just a normal int. This is assuming that head is just a normal reference. This is assuming that this is, I should say, okay, I messed up. It is this. My bad. But I'll tell you why. Yeah, I forgot. Head is also a pointer. So if you have a value, right, this, let's just kind of talk about this real quick. This is just a linked list pointer called this. And this gets implicitly passed in. That's what this tells me. I said this a lot. This L list : tells me that the L list pointer is going to get passed in to this function, if that makes sense. And really what I'm saying is the program, or the, I guess, the program being executed is going to have this as basically like the first parameter. And you don't get to choose whether or not that gets passed in because it's already being passed in. And that's why you don't have to define it here. But then this head is also a pointer, right? So the head at the memory data, this is a int. Let's just make sure I didn't make that mistake up here. I don't think I did. No. Okay. This head is a reference from the pointer of this to basically extract the pointer of the head, which we're then extracting the data field from. If I were to do this, then we're dealing with the address. And this is not going to be useful for us when we're talking about actually extracting things from the like the values that we're storing in the memory. This is a reference. This is a value. Okay. Hopefully that was clarifying something for somebody. Okay, so if this head's data is equal to D, then we can just delete the head. So what we would do in this case is we would say, okay, so we'd say new head is equal to this head next. Maybe we could reduce this. But then what we would want to do is actually delete the head. So we would, before we actually delete the head, I would say, let's make this old head. Old head is equal to this head, and then this head is equal to this head next. Okay, so really what we're doing here is we're taking we're saving a reference. This is like the previous to the current head, and we are then going to basically drop that reference from our list. But that doesn't save us from the memory. So now what we have to do is actually delete the old head. And that will save us the memory. Okay, that's base case. Okay. And also what we can do here, I don't know why I didn't do this, is we can return true. I don't even need an else because at this point we would have returned. So then we're going to set up the kind of same thing. So what we're going to do is we're going to say previous is equal to this head. Current is equal to this head next. I wonder, just trying to design this algorithm, if we have to do this, or if we could set the current equal to this. I think we can. Let me try doing something along these lines. Previous is equal to null pointer. Current is equal to this head. And then what we would say is I'll just keep it the way. It'll be more annoying to actually write out this head because we already checked that. We'll say current is equal to this head next. And then here we're going to say while this current is not equal to null pointer, and this next is not equal to null pointer. I think that's what we want. So we're basically checking, okay, as long as we have something, I don't even think we need the second part, because we could just account for that. Okay, so while the current node is not equal to null pointer, what we're going to do is we're basically going to check, is the current our node? If it is, we're going to delete it. If it's not, we're going to continue. Okay, and this will continue until we either reach the end or until we delete. So then in this loop, we'll have the base case, right? You're right. I am used to Python. Okay, so in this case, what we're going to do, and these two, These two are also node pointer. Thank you for that catch. Awesome. Okay, so in the basically the base case, right? If this current data is equal to D, right? We found our node at this point, and we need to delete it. So we have this reference to the previous, and we have the reference to the current. So in this case, here's what we're going to do. We're going to unstitch this, and then potentially unstitch this, and then potentially stitch this. But we're definitely going to unstitch this. So here's what we're going to do. We're going to say previous next is equal to null pointer, and then current next. We're going to say if current next. Why does that happen? If current next is not equal to yeah, you're correct. Okay. Current next is equal to null pointer. So basically, we're checking to see if we have a next. We do have a next. So in this case, we're going to stitch. So previous next is equal to current next. That's simple. And then what I'm going to do, our current next is equal to null pointer, and then now we're going to basically delete. So delete current. And I'm going to copy this and paste that into here. Because here it's implicit. Okay, so if current next is equal to null pointer, previous next is equal to current next is equal to null pointer, and then we can delete the current. This should maintain the structure of the list, and in this case, we could return true. That's probably what I want. Okay. Otherwise, we have some time still to actually find that node. I'm just going to say this, or I'm going to say previous is equal to current. Current is equal to current next. Okay. The last thing we need to do is return false. And in this case, our linked list would have no, how do you say, return. At this point, right, that value isn't even in the list, so we can't delete it. So real quickly, I'm going to save, exit. I'm going to more ls.cpp. We did miss one whole thing, but real quickly, because this is like less of the algorithm part, I'm just going to create a basic function to print the list. Copy. So it's kind of like a ChatGPT prompt. I'm just going to say create a function to iterate through a list given the head of linked list, and print the nodes in the list. Data next. I'm going to say address of this data next. So it's going to kind of go through, but it's going to have, so what we're going to do is we're going to create a new function here. We're going to nano HTTP. We're going to create a new function called print list, void print list. And then we're going to nano the CPP file. And in here, we're probably going to need to include hashtag include IO standard, not standard IO, it would be something else. SO string, what is the include for this? IO stream, okay. Yeah. You guys can tell how long it's been since I actually used C++ IO stream, or actually like really sat down and programmed it in C++. It's been a while. I do a lot of, hold on, let's see. Is this good? Should be. Awesome. Save that, exit. Okay, so now real quickly, because I know we're getting towards the end, main.cpp. I'm just going to say include list HTTP main. I'm just going to create a linked list real quick. Is equal to linked list. We're going to say list.add node 3 list.add node 5 list.add node 7 and list.add node 9. We're going to say list.print list. We're going to say list.delete node 5. And then list.print list, and then list.delete node 9. List.print list. Okay. List.add node 10. List.print list. Okay. So what we're going to do is we're going to start here. I'm just going to do this just to kind of show how you compile stuff. So G++ main.cpp -o main, and then linked list.cpp -o a.out. So there's an error, no declaration const. Okay. That's because we said that was const there. This current. Yeah, there is no current. Made a mistake. Let me just real quickly do this, just so we can kind of demo the two algorithms. I'm not going to spend too long going over these. Where did I say current? Current. There is no this current. It's just current. Make sure I didn't do that anywhere else. Okay, let's try compiling it again. I forgot that you need these. Let's try compiling it again. Linked list not declared in the scope. Of course, it wasn't. It should be a linked list like that. Undefined reference. So we never defined that. Nano. So I'll just quickly define that. Nano linked list, the HPP. This is something that you guys can try to do on your own, just because we ran out of time. Do that and then do a dot out. You'll see our list. Red has all of these. Let me nano main. So now what we're going to do is we're going to get rid of this print, and we're going to show what it would look like after that. So you can see we get rid of the 5. And here you can see, right, next is just 0, right? These are forward pointers, right? This is pointing here. This is pointing here. So the next thing I want to do is just get rid of this. We'll just do all of these now that we know that it works. Do that, run that, .a. And then here you could see, right, we do this, we do this, do this. Let's just more main. We have 2 print lists. It looks like it only printed one of them. Delete node 9. Oh no, it did both. Yeah. Okay, so we had the first list, right? After we deleted node 9, we should only have 3 and 7. And then we add 10, so now we should have 3, 7, and 10. Okay. I think that should conclude today. I can upload these codes to Canvas right now. I will also be uploading this video onto YouTube. I will share that link with all of you guys. And I'll post the link to that in the chat. If there's any other questions that you guys might have for me, feel free to ask those now. I'm going to get this up. But this is like a little project you guys can just take and kind of mess around with if you're curious of exactly how this works. And I would say kind of like for even practice with the knowledge that you have now, go through and try to implement the destructor class to see if you can delete a linked list. Because right now it's just leaking memory. Looks like there's no more questions. I'm going to stop the recording and stop sharing my screen, and we can end the meeting here. If I could figure out how to stop recording. Okay, there we go.